start this here. Close that up. All right. For a teeny bit of review from last day, I said, oh, well, maybe I'll leave it for next day. And then I said, we can do a little bit of conditional probability. So I'll just recap what we said, but it's from section 3. Is it 3.2? I want to say. We started conditional probability. So conditional probability is, well, things are no longer independent, right? We talked about independence last day, and we said, okay, if two events are independent, then knowing that one thing has happened doesn't affect the probability of another thing happening. So on the flip side of that, conditional probability is when knowing the outcome of one event affects the probability of the next event. Why is it so hard to write on here today? It's the same setup as always. Oh, maybe not. Maybe I did it twisted today. Liars. All right. All right. So what did we do to show that mathematically? We said, okay, well, we can have the probability of A given B, remembering that this vertical bar denotes given. And we said the formula is going to be, well, that's the same as the probability of A and B divided by the probability of B. How we read it is B had to happen before A happened. And so although we usually like to talk about A then B, in this case, B is the first event. All right. So here, B is the first event. And A is the second event. Right, the second thing that had to happen. So what we could do, or we, wait, a little jump there. Or we could write the probability of B given A, then A is the first thing that had to happen and B is the second thing that's going to happen. And we're finding that probability, that conditional probability of B. Thinking about the layout of the formula though, the top is the same, right? You read it as the probability of the first thing and the second thing, right? Whatever they are. So the probability of B and A, which notice that that's the same as up here. Right? And then now divided by the given probability, which in this case is A. So the reason I point that out is because you need to be really flexible, right? With your notation, A, B, it doesn't matter. They're just placeholders for the second event and the first event, right? And so it might make more sense to you to write it out this way, where A is the first event and then followed by B, but it doesn't actually matter, right? As long as you read it as the second event given the first event, right? Then the probability is the two happening together, right? Divided by the probability of the first event, right? Which is the same for both of those formulas because they are the same. All right. And we picked up an example that I've got here. We were talking about the 3 different treatment groups for, cocaine addicts, I think. And then we looked at whether they relapse or they don't relapse over some period of time. So we had some antidepressant desipramine or I don't know. Desipramine, I don't know. Lithium and placebo, I know how to say those. Right, and so then we have counts in each of these categories, right? These are joint categories, lithium and relapse, right? Lithium and no relapse, for example. And so we said, okay, if we know that a patient received the antidepressant, desipramine, what's the probability that they relapsed, right? And so now what you want to do is you want to translate that into that conditional probability statement, right? Because we're saying, okay, well, here we know that they received the antidepressant, okay? Now, what's the probability that they relapsed? So if we map that into the formula, right, and I'll scoot it up a little bit, we can rewrite that as what's the probability that they relapse given that they were given desipramine. Reading this formula just as the second thing and the first thing divided by the probability of the first thing, right? Then you don't need to do the mapping of the A and B's, right? As long as you kind of understand the shakedown of this, right? It's this and this divided by this, right? So we jumped straight to 10 over 24. What did I skip? I feel like I might have just been lazy or run out of time. I don't remember. Yeah, totally. So here, what if I just give myself a little bit of space here? This is the same. So the probability of relapse and desipramine is this joint category, right? 10, but 10 over 72, right? Is that probability of the two happening together. So it's really 10 over 72. And then I do a larger fraction just for my visual aid to see that I'm going to have a fraction over a fraction, right? And so then the probability of being given desipramine was what? Well, overall, regardless of whether they relapsed or not, was 24 out of 72, right? So here I get 24 out of 72. To keep it on the same slide, eek. I'm gonna write it here. I'm kind of squeezing it in to last day's notes. How do I deal with fraction over a fraction? I have to flip the denominator and multiply, right? Flip and kiss. And so you flip the denominator and you multiply it. And so now I like to take my fingers and actually put one on the 24 and one on the 72 like this, and then I flip it. Otherwise, I don't know. I have a hard time seeing it. 72 over 24, but 72 divided by 72 goes to 1, so that's why I'm left with 10 over 24. Which we were able to do with just the table, right? Technically, what we're doing is we're reducing these fractions, right? But you don't really need to, but it's good to know that that's, you know, technically what you're doing, right? How did we get 10 over 24 without doing these fractions? Well, we said, okay, if I know that they were given desipramine, right, that restricts the total to 24, right? So all of a sudden, I ignore everyone else because I know that they were in this group of 24, right? Now, how many of those relapsed? Well, 10 out of 24, right? So we can do it either way. And sometimes I do it this way. Sometimes I just look at it and it's whatever sparks a joy, I guess. But you can do it either way and you'll get the same answer. And I feel like, sorry, this was an extra slide, but it's the same, right? Let me just confirm here. I'm just gonna check against, there's no subtle difference here, right? If we know the patient, oh, they are different. Phew. They look the same, but they're not. If we know that a patient relapsed, so now the given information is that they relapsed. Okay. There, that's the difference. What's the probability that they received the antidepressant or the desipramine? Let's do it with the fractions first, and then just using the tables. We'll do both. Okay. So dealing with the fractions first, I want to, well, first thing I have to do is I have to map out what event happened first, or what's the given information, and then what's the thing that we want to talk about. And so here, if we know that a patient relapsed, which is the same as being given relapsed, is how you're gonna read that. Okay. What's the probability of desipramine? Probability of desipramine. Translating that into probability notation, it's going to look something like the probability that they were given desipramine, given, right, that vertical bar is given that they relapsed, is the same as the probability of desipramine and they relapsed, right? The two of them together divided by the probability of just relapsing, which is the probability of Desi, that's cute, and relapsed. Looks like Dury. Divided by the probability that they relapsed. So we're interested in the desipramine and they relapsed, which is 10 out of the 72 in this case, right? When I'm just talking about what's the probability that they were given desipramine and they relapsed, I'm not specifying any subgroups or anything like that. So it's over the 72. So that's going to be 10 over 72 divided by the probability that they relapsed. Now, the relapse is going to be, regardless of what treatment they were given, it's going to be 48 over 72.
Can I ask, why is it 10 over 72 instead of 10 over 48 total amount of relapses?
The answer is 10 over 48, but the probability of relapsed is the 48 out of 72, and the probability of just the desipramine and the relapsed is out of the 72. Because we're not talking about knowing that they relapsed here. It comes from that. But when I break it out, then I don't care. I don't have any given information anymore. So it makes it easier to deal with. But yeah, the final answer is going to be 10/48, right? Which you can just grab from the table if you want. 10/72, flip and multiply 72/48. I'm going to write across here because I'm running out of room, is 10/48, which is the same as if you just focused on, okay, now I know that they relapsed, reducing my total group to 48, right? Now, what's the probability that they were given desipramine? It's going to be this 10/48. Or using the table, the probability of desipramine given relapsed is 10/48. Oops, that doesn't look like an 8. Same answer, just different ways of getting there. Yeah.
I guess if you didn't want to show it, the 10/48 or like partial marks.
I'm good with using the table.
Okay, so you don't have to do like all that fraction stuff.
No, if you don't like fractions and this way makes sense, that's fine by me, right? On a test, I'll give you a table, I'll ask you what these probabilities are, and it doesn't matter to me how you got there, right? The answer is the same. Of course, I do give part marks for correct work. So if you're trying to show work, then this kind of the fraction way is more reliable that way, right? You've got more to show. But you can always confirm it by just looking at the table too. But you don't have to show the fractions, right? It's all good. You're good. So you are probably just going to do this, right? And that's fine. I'm fine with that. All right. So why did I show all that work? Why did I spend all that time? Oh, it's my job. There might be someone out there who wants to use the fractions. Maybe. So we can look at all these given probabilities, right? If we wanted to, the probability of lithium given relapse, the probability of placebo given relapse, then you can confirm those, right? Both with the fractions or just looking at the tables. Either way, you're going to get the same answers if you're doing it right. Okay. So what we said, was it last day or maybe the day before even, probably last day, was that, okay, if two events are independent, it was last day. If two events are independent, then we said I'm allowed to say that the probability of A and B is the probability of A times the probability of B. I also use it as a way of checking to see if A and B are independent, right? If I have the probability of A and B, I have the probability of A and I have the probability of B, I can multiply those two, and if they end up being the same, and it has to be exactly the same as the probability of A and B, then they are independent, right? So that's how I tend to use this formula. Because what do we have to be really careful of? Well, what if these are not independent anymore, right? then one's going to be conditional on the other, right? And so what happens is that if we want the probability of A and B, and I'll highlight this in pink here. We need to find the probability of A given B times the probability of B. What's that assuming? That's assuming that B was the first event, right? Because A has to depend on what happened in B. And so here, where B is the first event in this case, if you want B to be the second event, how would you have to rearrange the formula? To make B the second event, the probability of A and B is the same as B and A. Okay, so that part's fine. But it would have to be the probability of B given A times the probability of A. We've seen this formula mere moments ago, right? We've just rearranged it. So here, notice that the probability of, sure, I'll use B given A, is the probability of B and A, or A and B if you want, times, or, oh my gosh, I jumped, divided by the probability of A. What have I done? What have I done? I've just multiplied the P of A over and solved for the probability of A and B. A and B. The and makes them interchangeable. And what did I do? I just multiplied this over to solve for the probability of A and B. Now, this note is, of course, referring to how the formula is written here, right? But whatever is the given part is the condition, okay? And whatever's on this other side is the thing that I'm interested in, right? Conditional on B, or in this case, conditional on A, right? Doesn't matter. Okay, good. Hello? As an example, what if I have this distribution of gender and major of students in an introductory statistics class? So they're either a social science major or a non-social science major. Disjoint events, right? Can't be both. Either are or you aren't. All right. And then males and females. Now looking at this, just looking at the table, would you say that these are independent or not independent events? I would probably say that these look pretty independent. Why? The counts look the same, right? For females, 30-20, 30-20, for males and females, but also within the groups, 20-20, 30-30, obviously, within the groups. That tells me that these are probably independent, right? Because it doesn't seem to depend on what your gender is, doesn't determine the distribution of the major, and same thing with the major, doesn't seem to distribute the gender. So we can confirm it a randomly selected social science major has a probability of just 60 over 100, right? So 0.6. Okay, that's fine. So that's P of S, let's call it. Hmm. The probability that a randomly selected student is a social science major, given that they're female. Okay. We can use the fractions, but let's save ourselves some time here. So the hard part, I think, is picking apart this sentence to figure out, I'll close it there. What part is what part in the probability formula? So here, I want to know, oh, they've used S, but let's use the probability of S given that they're female. Okay. Because we were given that they were female, and so that's the second part of this conditional probability, right? And we want to find what's the probability that a randomly selected student is a social science major. I've used S, they've used SS, but here I'll just make it match there. From the table, if I asked you to find the probability that a randomly selected student is a social science major, given that they're female, what are you going to do in terms of the table? No fractions allowed. I've been given that they're female, and so I'm restricted to this region. Now my total is out of 50, right? And so 30 of those were social science majors, and that's where the 30 over 50 came from. $30 over 50 is 0.6 again. So here, if we take these two together down here, then since the probability of S given F is the same as the probability of S, what does that mean? It means that the major is independent of the gender. We conclude the major is independent of the gender. Most of this course is going to be me saying, well, intuitively, you know, you can look at this table and say, I've got a gut feeling that these things are independent, right? But then I give you mathematical formulas for you to back it up, right? And so that's what we're doing here, right? So here, you were able to look at this and maybe not put your finger on why you would say that they're independent, right? But mathematically, this is why, right? Because the conditional probability, it actually doesn't depend on the gender, and it ends up being the same as just the raw probability of being a social science major. Yeah. So what we just saw is that if we have something like P of A given B, if it just spits back the P of A, right, then it doesn't depend on B, right? It's not conditional on B. And so here, this is what we did, but not this fancy, but it is what we did technically, right? If I have the probability of A given B, I can rewrite it as the probability of A and B over the probability of B. That's fine. That's just the formula, right? if A and B are independent, then I know that the probability of A and B is the probability of A times the probability of B, still divided by the probability of B. Well, probability of B divided by probability of B is just 1, right? Multiplying by 1 spits out just the probability of A, right? But this is only true. This is equal to this if, I want to say if and only if. Are you guys okay with logical statements like that? IFF is if and only if. Only if. A and B are independent. Let me take a sneak peek. Okay, great. That is what I wanted to do. What a surprise. So what's going to happen with these conditional probabilities is often there's going to be a first event and a second event, which is what I've introduced kind of on the slide, right? But when that happens, the easiest way to organize the information is with a tree diagram, right? And so for conditional events, or for, yeah, conditional events can be thought of as a first event followed by a second event. The easiest way to organize information is going to be using a tree diagram. I'll write that down. The easiest way to organize information, or organize this information, is using a tree diagram. I like to do it like this. This is the first event. If the first event has what? 2 possible outcomes. I could have more than 2, but it makes my tree really big. So for illustration, I'm only using 2 possible outcomes for the first event. And then what happens? Well, let's say what's something? I draw a red card, or are you guys okay if I say I'm not a red card? There's a method to my madness there, right? I've got red and black cards in a deck of cards, but it's easier to think of if I draw a red card or not a red card. Okay, so now what happens to the probabilities, right? We're not going to focus so much on the probabilities here, but it's just to illustrate. If I want my second event to be heart, right? Then if I've drawn a red card already, that's going to affect the probability of it being hearts, right? It reduces the probability because I could have already drawn a heart, so now there's fewer of them, right? And so here, if I want, so the first event is drawing a red card. Then the second event, let's do it in green. I draw a red card, second draw it. Well, it either is a heart or it's not a heart, right? And it doesn't matter if I drew a red initially or not, right? I have the same outcomes to choose from no matter which path I went down. So what happens is the second event second event is drawing a heart. So here it's either a heart or not a heart, heart or not a heart. Okay. So this is the general layout of a tree diagram, which without numbers is kind of confusing. The sound of the air is distracting me in the hallway. It's weird. Yeah.
I'm confused by why in the second event, after you've drawn a not red card,
Yep.
The option exists to draw a heart. Wouldn't both of those potential outcomes be not a heart?
Yes. So what I've avoided is adding the probabilities underneath, which is what we will be doing. So underneath here, so exactly. So if I didn't draw a red card, what's the probability of drawing a heart? 0. There's none there, right? Unless, oh, now I'm, maybe I didn't phrase the situation right. So it's not, yeah, the second event, so it's from the same deck, sorry. You're right in that situation, if I'm drawing from what I drew before, but in my mind, we were drawing from a deck. Was it a red? Yes or no? And then that sets me down the path, and then I draw a second card from the same deck. Nice, thank you. Sometimes the probability can be 0 though, so you just have to stay on your toes. But let's do an example with numbers so we can see how this works. Okay. All right. Are any questions about that before we do? Okay. So here we're given a lot of information. Okay. So the American Breast Cancer Society, or I guess I said breast, that's weird. American Cancer Society estimates that about 1.7% of women have breast cancer. I knew it was a breast cancer example, but that's weird. And then, so blah, blah, blah says that, how do I, mammography correctly identifies about 78% of women who truly have the breast cancer. And then an article published in 2003 suggests that up to 10% of all mammograms result in false positives for patients who do not have cancer. So there's a lot of layers going on here, right? And so obviously there's a note here, these percentages are approximate and also dated 2003. Hopefully we've improved a little bit, maybe, who knows? If you had to decide, so I'm gonna tell you as a fact, these are conditional probabilities, right? And if our goal is to build a tree diagram, then what would you pick as your first event and your second event? Okay. It's not obvious, so I'm going to tell you. I'm going to do, they either have cancer or they don't have cancer. And then whether they have cancer or not is going to tell me the probability of testing positive or testing negative. Okay, now where did I get that order from? Okay, where did I get that from? Is this last one. Okay. Mostly. Okay. But also the second one, I guess. Sure. Let's start with the first one. Why is the cancer the first part, the first event, and not the second event, right? You can test positive, you can test negative. either have cancer or you don't. That's another way of setting up the tree diagram. But given these probabilities, right, this is the same as given that they have cancer, given that they have cancer. And that's my clue that, okay, then I need to know if they have cancer or they don't have cancer with some probability, right? And then I can apply these probabilities. And so same thing here. 10% of all mammograms result in false positives for patients who do not have cancer. Well, so now we're given that they don't have cancer, but they tested positive, right? And so again, this is another clue that so given that they do not have cancer. Now, did I give myself room here? Let's just spend some time. I'm going to give myself another page here. Dink. And this is a lot of information here. So what I want to do is just break it down and kind of, okay, start with a tree diagram. What's nice on the test is the first part of the question will say, make a tree diagram to show these probabilities. And that's going to obviously nudge you in the right direction. Okay. And so part A, I guess, make a tree diagram showing these probabilities. I'm going to start nice and slow here, right? I just decided from the wording of the information that I was given, we decided that whether you have cancer or you don't have cancer is the first event. So, oops, how about cancer or not cancer? Let's see, have cancer be the first event. I think we can all be convinced that if you have cancer, the probability of getting a positive test result, which is actually negative, right? Negative in like a sad way, is higher, hopefully. Otherwise, your test isn't doing anything. It's like flipping a coin. Yep, sorry to say. Right, and so here, depending on whether you have cancer or you don't have cancer, that's going to impact the probability of getting a positive test result, right? And that's what we're relying on when we read test results, right? And so what were we told? In general, they estimate that about 1.7% of women have breast cancer. So the probability of having cancer, or if you think of it as the probability of going down this branch is 1.7%, or since we're going to be doing math, we should use the proportions. And so this is going to be 0.017. Now, this gets a little heated in here. What's the probability of not having cancer? Knowing that the probability of cancer is 1.7%, then this probability is going to be 1 minus that, right? It's only 2 possible outcomes. It's the entire sample set. And 1 minus 0.07 is, do I have a cheat sheet here? I do. Is 0.983. 1 minus 0.017. As a side note, these must add to 1. Right? Or if you have more than 2 branches, when you add them all up, right? Because that's your sample space, those have to add to 1. All right. So now we're getting into the second event. Okay. So you have cancer, and so we're down this branch here. You're either gonna test positive or not, right? And so here, P or not P. And so here I'm gonna let P be testing positive. Be the second event. Okay. If you don't have cancer, you can still test positive, right? We've heard of false positives, right? And or you can test negative, right? Or not positive. And so hopefully the probability is quite low, but it is there, right? And so regardless of which branch you're going down, you can test positive or not positive. The reason that I'm saying not cancer, not positive is because otherwise it trips people up and you want to make more of these branches than you have to, right? And so if you just reduce it to a yes or no type of situation, then it is a little bit easier. Okay. Going back to this information that we were given. We're going to test positive. So the probability of testing positive, given that they have cancer, right, is 0.78. Okay. So here, let's write this out. This tells me that the probability of testing positive, given that they have cancer, is 0.78. Okay. And so the probability of testing positive, given that they have cancer, is 0.78. Oh, let me write that so you can see it. That helps. Notice that this is a conditional probability. Now, if these were independent events, these probabilities wouldn't change, right? I flip a coin, I toss a head or not a head, head, not a head, head, not a head. I can keep going. Those probabilities aren't going to change. So that's a nicer tree diagram to deal with. But usually we're using it for conditional probabilities. But you can use it for independent outcomes as well. Okay? Because what would happen then? Probability of P given C is just the probability of testing positive. Okay. What's a fact? These two branches have to add to 1, right? Because we've already headed down this route. We have cancer. Now you're going to test positive or not, right? And so here, these must add to 1. So we use that to find this probability, right? 1 minus 0.78. So the probability of not testing positive, given that they have cancer, is 1 minus 0.78, which is 0.22. With my cheat sheet, I should pull it up better. It's so small. All right. We're doing good. All right. So what's the next part? 10% of all mammograms result in false positives for patients who do not have cancer. So same deal here. This is the probability of testing positive given that they do not have cancer is 0.1. So here, the probability of testing positive given that they don't have cancer is 0.1. Again, of course, these have to add to 1. So then this probability, the probability of not testing positive given that they don't have cancer is 0.9. Okay. We can use this to find probabilities now. Okay. And how we're going to use this is if I go down this branch, for example, how am I going to read this? It's a patient that has cancer and tested positive, right? Whenever I'm saying and, you're going to be multiplying, okay? And so if you multiply down this branch, what's going to happen? You're going to find the probability of a patient having cancer and testing positive by multiplying down this branch, okay? And so here, and maybe what I'll do is I'm going to just snag a copy of this. So that way I'll have it in case I need it. Just the backup. Oh, that's nice for you, Emily. What a cheat. I know. Okay. So here, if I start up here and I go down this branch, okay, then how I'm going to read this is at the end of this branch, I have the probability of cancer, or maybe I'll just write C just to save us some space. The probability of C and positive P. From the conditional probability formula, I know that the probability of C and P is the probability of what was the P given C times the probability of C, right? Just multiplying down the branch. Some rearranging, but I think you can convince yourself that that's true. Multiply down the branch. So what I could say is, okay, I can multiply down all these branches. So cancer and P, cancer and not P, right? Not cancer and P, not cancer and not P. Okay. How I kind of short form show this when I'm writing, and let's see what's a color that let's use purple, is instead of writing the probability of C and P, I just write C followed by P, C followed by not P, not C followed by P, and then not C followed by not P. Okay. It's just a guide for me to figure out what happened down all those branches, right? It's just a summary of what happened down these branches. Now, if I multiply down, and I do have a Martha Stewart version here where it's already pre-baked, if I can read it, 0.017 times 7, 8, I get 0.0133. 0.017 times 0.22 is 0.033. No, just one. I'm squinting here. 0.0037. You can confirm. Yikes. 0.983 times 0.1 is 0.0983. I can get on board with that. And finally, 0.983 times 0.9 puts me at 0.8847. Yes. Nice. Must add to 1. Why? I've just listed all the possible combinations, right? Nice. So, cool. I know it's kind of an overwhelming tree, but you don't have to do these last ones. I just find that if I just do them and get them out of the way while I'm on a roll, then I can just grab the probabilities that I need, right? You don't need all of them to answer the questions, but it's just nice to have. So in terms of what you are expected to show on your tree diagram, it's just this. And maybe I'll even, this is helpful, but you don't need to have it if you don't like it. Okay. A complete tree diagram. If you are wondering kind of how far do I need to take this, right? There's a lot of extra steps. I take it all the way because that's just how I find it easier to deal with. And then I read the question and I figure out what I need out of there. But at least I've done all the work. Just depends on what you like. Okay. So a key thing here is, all right, when we read down here, down this branch, we were saying and, right? Now, so here, I'll just write a note. And means multiply. What if I have, there's a question that I'm leading up to. What's the probability that, well, I guess I could do it. I'll go there. So when a patient goes through breast cancer screening, there are two competing claims. The patient has cancer and the patient doesn't have cancer. If a mammogram yields a positive result, what's the probability that the patient actually has cancer? Okay. So what I'm gonna do is I'm gonna take this tree and figure out what I need from there to answer this question. And sure, I'm gonna copy it all and remove some stuff. Or a lot of stuff, I guess. Do this. We don't need this reminder. I guess that's not part of your complete. Oh, it's gonna look so good. Nice and clean here. Let's do this. There. Okay. First thing we need to do is figure out what this question's asking. That's kind of a big step, yeah? So if a mammogram yields a positive result, that's the same as being given that we had a positive result, right? So here, given a positive result, what is the probability? Find the probability of cancer. In terms of probability notation, what does that look like? If I again, let P be a positive result. Oops, I'll use a capital P. Using the same notation, obviously. Otherwise, what a mess. Find, let's see, be cancer. In terms of probability notation, what am I trying to find? I want to find the probability that they have cancer given that there was a positive result. One thing that I want you to see is from the tree, right? That's why we mapped these things out, is there were two ways of getting a positive result, here or here, right? So I like to just kind of highlight the branches that give me a positive result, right? And what I'm also going to note is it's this or this. Now, or means addition. That's how we find the probability of a positive result. Why do we need that? Well, if we go back here, then if I rearrange this, then this is the same as the probability of C and P divided by the probability of P. So from here, the probability of P, just overall, right, regardless of the cancer outcome, is going to be 0.0133 plus 0.0983, which is something I don't know. Does anyone have it?
6.
Point 16, sorry. Nice. Awesome, thank you. And that's what I'm gonna use up here. I already have the probability of cancer and positive, right? We're looking at cancer and positive. I already have it as the probability is 0.0133. So from here, I have 0.0133 divided by 0.1116, which is, I'm gonna say 0.12. Hopefully these pre-baked notes are right. You can use the tree diagram to answer lots of different conditional questions, right? And so mapping it out is probably it's tedious, but it's the safest way of figuring out these probabilities, right? And just as long as you remember that as you're going down the branches, you're multiplying, and then at the bottom of the branches, it can be this or this or this or this. And so then you're adding up the probabilities that you want. right? And that's why they have to add to 1 as well, right? This or this or this or this, well, that's everything that could possibly happen. So it has to add to 1, right? Okay. I think we just solved this. That was sloppy. Don't need that slide. Yeah. Yields a positive result. What's the probability that they have cancer? So the probability of C given P, which we already found, but it's just got the tree diagram. Sometimes if you prefer to write the tree diagram this way, you're welcome to. The only reason that I do them like an upside down tree, I guess, is because then I can map out my space easier. But if you're typing, it's easier to go this way, right? But then you need to make room above for your branches, which it can get kind of tricky. But you can confirm that these are the same trees, just nicer. Suppose a woman who gets tested once and obtains a positive result wants to get tested again. In the second test, what should we assume to be the probability of this specific woman having cancer? So now, this is what? This feels like the question we just answered. It's just worded differently, and it is, right? And so let's break it down. So we know that they tested positive. So given P, what's the probability of C, right? P of C given P, which we just found was 0.12 from earlier, right? I'll just say in general, this is another way of phrasing the question, which is good to see. Of phrasing the same question as before. Yeah. What's the probability that this woman has cancer if this second mammogram also yielded a positive result? Okay, let's see here. Should I nab our trusty tree again? Maybe I'll grab this beautiful tree. So now, what were we finding before? That's confusing. We want to find the probability that they have cancer given a positive result.
From 2 tests.
Yeah. this is wrong. From the second test, where's the? Oh, okay. See here, positive on the second test. Okay, whew, I got there. What changes? The probability of having cancer has changed, right? We just decided that after a first test, the probability of cancer, knowing that they tested positive on the first one, so now that alters the probability of having cancer to 0.12 in this tree. So here, this changes to 0.12 and no cancer, there we go, changes to 0.88. Right, so it alters those probabilities, but the positive and negative conditional probabilities don't change. So now the second test is being taken into account in the tree rather than the calculation up here. So then the calculation stays the same. And so we have the probability of C and P. And now let me see if I can, oops. How do I get a different color here? I want it to be white, maybe. Because these are wrong now. Fine, I'll just cross them out. Over the probability of a positive. And how am I doing? Okay. So now I can multiply down these branches and I can find, and I'm going to steal it again, 0.12 times 0.78 is 0.0936. 0.12 times 0.22 is 0.0264. 0.88 times 0.1 is 0.088 and 0.792. See if I can give myself some more room here. There. Probability of cancer and a positive is 0.0936, just from the tree. Divided by the probability of a positive result. Now a positive result is here or here, right? And so in the denominator, what do I have? I have 0.0936 plus 0.088, which is gonna go with 0.52 from these notes here. Something that trips people up sometimes is having the value in the numerator, but also appearing in the denominator. But notice you can't cancel these because you're adding in the denominator, right? And so you have to absorb them into one value and they don't cancel out. And just like that, man, multiple choice questions can be difficult. Yeah, a lot of work went into that. Okay. Any questions about that one? No? None. Just need time to sleep on it a little bit. So what we've been doing is technically called Bayes' theorem. It's in the slides. I'm not going to talk about it. But here's kind of a cute application activity. Give it a whirl. And I think the answers are in here, so you can check it out. And I won't see you for a whole week. Oh my gosh. Have a great long weekend and see you on Wednesday.